So our next speaker is Dennis Sylvester. He's from the University of Michigan. He's in ECS. He's been there since 2000, I think, and before that he did his PhD at UC Berkeley.
Thanks. Thank you, Boris. So it's a pleasure to be here. It's great to be one of only a handful of academics here, among a lot of people actually really doing real systems and products. So I'm going to talk about something that Bill sort of introduced for me. Largely, this is a starting point for some of the work we're doing, but I'll start here with this slide that talks about Bell's law. So Gordon Bell's law is not as well known as Gordon Moore's law, but in general does talk about a new class of computing systems that arise roughly every decade, and these systems tend to be smaller. They tend to be cheaper, and they tend to be much higher in terms of sales volume potential. And although it's a little bit small, you can kind of see over the span of the microelectronics industry that this is roughly held true, bringing us today to the post-smartphone era. You'd say maybe IoT would be the next generation beyond that. Now, IoT kind of breaks us a little bit, because if you look at the examples, at least that I picked of IoT, maybe some of the more successful examples, they're not particularly smaller than smartphones, right? The Nest devices, this is one of the smaller Echoes, obviously, the wearables. Wearables are maybe a little bit smaller, but they're also not extremely cheap. They're on the order of $100. You're not going to get to trillions of devices like people talk about from IoT if your devices are costing $100. It just doesn't make sense, right? So, we do need to get these things to be smaller, to be cheaper, in order to get that sales volume up, in order to really instrument the world, right? So this is why I'm kind of referring to things now as sort of the next generation of IoT being more of an IoT squared, Internet of Tiny Things. These things need to be smaller, and actually, obviously, that co-aligns with the name of this summit, which is tinyML, obviously. So the key constraint, when you get the devices small, you can see as you move from mainframes and workstations down to smartphones, again, orders of magnitude lower power consumption, just because the size, right? You need to be smaller either for battery purposes in the latter stages of this slide, or earlier stages just for cooling and things like that, right? So we need to get that power way down. So we just heard a nice, really interesting talk about always on vision and a milliamp or a milliwatt. We're trying to push that number obviously a lot lower. So how low do we want to push that? So this slide is a very simple slide I've used for a long time, just calculations to show you if you want to have a device that is consuming or that is living or has a lifetime on the order of a year. Now there's rechargeability and so on you can worry about, but let's just say I want to live on a coin cell, a small coin cell, because they have different sizes, obviously. 5 millimeters, about as small a coin cell as you can get. And you want to live for a year, you're going to have to be at the top of this red circle, which I've drawn, which is about a microwatt of average power draw. Okay. If you want to go to an even smaller battery, like the thin film batteries that we often use from companies like Symbet, it's orders of magnitude worse than that, just because of the volumetric density of that device is not so good. So we're talking about now nanowatts, maybe up to microwatts. So let's call it tens or hundreds of nanowatts is the kind of power budget that I'm interested in, okay? So that's what I refer to as ultra low power. If you look at microcontrollers, they consume, when they're running full out at, let's say, tens of megahertz or hundreds of megahertz, they're going to consume way more than that, obviously. So you're going to have to be doing some duty cycling along the lines of what Bill was referring to. You need things that are going to wake up the system to do interesting tasks when interesting things are happening. So this is really the idea. This has been touched upon by Marion's talk, been touched upon by, obviously, the Qualcomm talk. You want to basically have something that detects something interesting and then wake up Big Brother that's going to do something at a lot higher power level with a lot higher fidelity or accuracy or interest level. So if you look at, for example, this is consistent. You say, what's the standby power of a microcontroller? And I thought about this when the question came out from the front row here for Bill's talk. Yes, you want to wake up a big system, a Big Brother system, but how low power can I put that Big Brother system? If I have a 1 watt device and I put it into a sleep mode, typically that thing's still consuming microwatts, okay? So if you look at these best available microcontrollers, their standby power is on the order of 100 nanowatts, roughly speaking, deep sleep type modes. They wake up on the order of tens of microseconds. That's pretty quick. Even when you're talking about 30 frame per second type vision applications or audio applications, not a lot's happening in 10 microseconds. My point here is I can have microcontrollers and other types of things in deep sleep mode if I can be comparable to their power budget in what I'm doing as my wake-up mechanism, then I'm doing pretty well. If I'm way above that, I'm dominating. If I'm way below that, I'm wasting, right? I'm not taking advantage. So that's kind of where I'm starting at. So what we've been doing at Michigan for quite a while now is we've been building this platform. And so this is one of the key messages I want to make to this audience, many of you who I don't know, to say that we've been developing this sensing platform, which is a really interesting platform, I think, for the introduction of intelligence or machine learning onto it. And we've been working on that as well, and hopefully we can work with you all on it. The idea here is that basically we're trying to get to really tiny form factors, millimeter scale type of form factors for an entire system. We have a sort of a staircase, you can see, type of platform where we have multiple chips. The package and the printed circuit board and things like that are largely gone, okay? We do have some encapsulation. I'll show you pictures maybe of that. But it's a modular die stack structure where each layer in this system has a functionality. It could be power management, it could be communication, it could be the brain of the system, it could be a neural network in hardware. Certainly there's other elements in it as well. So we have this system that allows heterogeneous technologies. I can put in the latest, greatest embedded non-volatile memory in one layer if I'd like, or I can put in ultra low power analog front end in another layer in a whole different technology, like an old technology like 0.18. Okay, that's a very old technology. We use it a lot because it is ultra low power in terms of standby power. So this is a platform that we're using, and this is a list of sort of the types of things that we can do or have developed for this node so far. So these are the things we have in our back pocket, and now we're trying to introduce more intelligence and more interesting things onto it. So we can do communication. In the more interesting one here would be that far field RF. This is something that can talk from a tiny node to a base station, not node to node, okay? So these distances listed here are to a base station. And you can see that, they're fairly far for the size device we're talking about. We do some things in the optical communication space as well. We have energy harvesting capability, mainly through photovoltaic or solar, whatever you want to call it. And it's largely optimized for indoor lighting, which is where a lot of these devices might be used. Okay, very different spectrum than outdoor. We use ARM-based microcontrollers, sort of their lowest end microcontroller, because we have such a stringent power budget. And then we have these embedded flash modules that we've co-developed with TSMC in many cases. So the applications supported are listed here. The bottom one is bolded because that's what I'm going to talk about for the rest of the time. So this is an early audio system that we built. It's one of our bigger systems. There actually is a little tiny PCB in there, so we haven't completely gotten rid of it. But you can see kind of the complexity compared to the first picture I showed you. There's a lot more layers. There's a lot more to it. We have photovoltaic cells on the top here. We have a 3D magnetic antenna. And then we have a MEMS microphone for audio acquisition. And this is done in conjunction with TDK or InvenSense originally. And we've worked very closely with them to develop our systems jointly with their MEMS microphones. These devices are very small. They strip out all the active electronics and they give it to us as a membrane. And we say, okay, now we take it from here and do all the signal chain. Okay. And so this has worked pretty well as a starting point for our audio. But then the N0 program came around, okay? And we said, let's not just record these, sound. Let's do something intelligent with it. And this is the program that Bill talked about. And basically the idea there was, as he said, just basically wake up on detection of objects in your environment. Now, we can choose different sensing modalities for that program. We chose acoustic because we had that microphone in our pocket and we thought we could listen very, very cheaply. Okay, so the question is, how do you listen very cheaply? For instance, to identify an object in your environment, the first thing you might say in the audio domain is that I'm going to do an FFT of the spectrum, and I'm going to look for features or the presence of energy at different frequencies that indicate that, oh, there's a car nearby, because a car has an audio signature, right, which we can detect, and we do the same thing in our brains and then through our ears. But I really need to know the frequency content, right? So you say, okay, I'm going to do a full FFT. I've just destroyed my power budget by doing a full FFT of the audio spectrum, right? So what we did was we looked at the targets of interest from that program, in that case, as Bill said, generator, truck, car, and we found the spectrograms to look something like this. So you can see it's hard to see here, but this is frequency on the y-axis here, and this is time domain across here. So there's stationary signals, which helped us a lot. But also there's a handful or a small number of frequencies of interest for each target, okay? Now you may say, well, not every truck sounds the same, obviously. What if the truck's warming up? What if the truck it has some engine problem and you can diagnose that? Well, that's all interesting extensions to the work. But nonetheless, this is the data that we were given, and we said, well, there's frequencies of interest. If we could just detect the energy content in these small number, let's say 8 or at most 16 frequencies, we don't need to do a full FFT for that, okay? We also noticed that the frequency content was relatively low. So of course, we know we hear at best, I don't anymore, but 20 to 20 kilohertz, right? And so you might say, I have to look at that frequency range. But for these devices or these objects, we could look at basically sub 500 hertz components. So that means we could sample at 1 kilohertz to do Nyquist sampling. So basically, this allowed us to run everything at a lower clock frequency, including our ADCs and our digital, to bring our power down as well. So you find all these little tricks and you say, okay, now I can do that and bring the power way down. Now I have an animation here that I'm gonna blast through real quick because it's really not, it's not ML, it's not the most important thing. It is what allowed us to meet the 10 nanowatt target of the system, but it basically is a way of extracting features, and we use this serialized tone of interest approach instead of this full FFT where you do all frequencies at the same time. We did them serially to reduce our hardware requirements. We also exploited a latency constraint that was given to us in the application. And so the point here, key point to generalize here, is that the application has to drive a lot of this, right? So we were told, you don't have to detect this thing within 10 microseconds, or even 1 second. You can take 10 seconds or maybe even slightly longer to detect the presence of a generator or a car or a truck. We use that to bring our hardware and our power requirements way down. So depending on the application that you're interested in, there might be similar ways to try to exploit that looseness or lax constraint to try to bring down hardware costs. So I'll skip through this animation because I've sort of summarized the general idea, but we do get 30 to 50x power reduction by doing it this way over a full FFT, which would be the straightforward approach. So then we take that feature extraction, which is always going here in red, and we basically then activate our classifier, okay? And we started with an SVM classifier in phase 1 of the work and moved to a very small neural network for phases 2 and 3. And the idea is that the classification doesn't have to always be going. We always have to be listening, okay, because we don't want to miss something, but we can make a decision every once in a while. And this allows the classifier to be power gated and powered down and be more complicated, therefore, because it's only used once in a while. So this is another example of something that might be generalizable to say, hey, your classifier may not always need to be making decisions, so you need to figure out how often it needs to be deciding things, and then you can figure out that duty cycle and how complicated you can make your classifier. So this is something we also exploited to try to make the decisions more valid, but without killing our power budget, okay? So this is one example of one of our neural nets. There's just a few layers here, some fully connected layers, some nonlinear functions in between, just like any sort of traditional neural network. It's small. I think on the next slide or two, I have some examples. You can see an example there, 7.7 kilobytes is the parameter size in one of our systems. This is our Gen 3 system, which is one of our more complicated systems, if you want to call it that. Still very small, obviously. And this is why we're able to get the low power, okay? And this is some of the results. The top right is what Bill kind of already showed briefly. Because you're all getting the slides, I'm not going to spend much time here. I want to say a few other things before I run out of time. Basically a rock curve, picking, this is an example of this type of application you're using as a wake-up mechanism. You might want to err on the side of false positives, right? Because you don't want to miss things. So, optimizing that rock curve toward the application or what use model you have makes a lot of sense here. So briefly on voice, I'm at 15 minutes. So we decided to extend this to voice activity. And if we want to take that same 5mm coin cell battery and we want to last a year, that power budget is 650 or a little bit below a microamp or microwatt. Okay, so this is what we were shooting for, and basically the system we wound up with is about 140 nanowatts, always on voice activity detection as a wake up trigger for, let's say, the next big brother system, which for us would be a full audio recording, and potentially you could do keyword spotting, or you could do maybe some basic commands. This is what our current work is. Maybe there's a set of 10 commands that I could tell a device what to do. So it's very, very, very lightweight NLP, I guess you might call it. But so this is the system that we wound up with. So it's very cheap, 140 nanowatts. And I'm not going to go through this diagram in detail, but the key challenge for us was voice activity. Human voice is a little bit higher frequency than the previous things that we talked about. 1 or 2 kilohertz is where a lot of the action happens, but you can't rely on just going below 500 hertz. So we said, okay, let's look at the 4 kilohertz bandwidth, because that's pretty much capturing all important human voice activity. So that means we need to sample at 8 kilosamples per second. So now I've gone from 1 to 8. So everything in terms of the dynamic power of the digital stuff is going to be 8x, and that's something we didn't want to do. So we actually ended up mixing down. You can see at the top chain there's a mixer between the low noise amplifier and the rest of the signal path. And that mixer mixes down to about 250 hertz intermediate frequency, and basically allows us to then use the rest of the chain at a lower frequency. Now it brings in aliasing and some other artifacts, okay, which is common when you do mixing, if you don't do it in a certain way, which is complex, which is more power hungry. But what's nice here was that the neural network, we just trained the neural network that follows with the aliased information, and that allows us to basically sidestep a lot of that. So that's something that we did. And the neural network, which is kind of buried in this far right figure here, includes these size layers. So very small, and 4-bit weights. And this is what we wound up with 140 nanowatts. And the results here, just to show you an example, I have two curves here, basically saying, well, we took this LibreSpeech data set, we mixed it with some noise at different SNR levels, and for 10 dB SNR, we got about 90 to 92% hit rates. And again, you can modify this toward more false positives or what have you if you'd like, okay? Now we actually put this into a sound chamber and actually did speech as opposed to just electrically sending a voltage signal into the LNA, which is what we think the speech looks like post microphone, okay? This is what most papers, academic papers, will do. But if you actually go and you actually play sound in a sound chamber, you get worse results. So full disclosure here. And we got something like these numbers here. Normal speech at a meter is about 65 dBA, and you can kind of see where we're at there, okay? So this is where we're at currently in extending that. And I'll skip this slide and say that, a couple takeaways. I think the first bullet we largely agree on. I've got an imaging talk before me and an imaging talk after me, but I think I've heard enough people talk about keyword spotting and audio today already that, it's definitely a really interesting area. And the power budget is more in line with tinyML to me personally. Neural networks don't have to be deep to be effective. This is something that we're trying to explore. And just skipping to the bottom, we're trying to build really low power classifiers for interesting tasks. So if you have applications that are of interest to in that space, we'd love to talk to you. We've done a lot of tech transfer. Ambic Micro and Mythic both came out of the group. So if you know those companies, so we're very interested in that sort of thing. So I'll stop here and take questions. Thank you.
Thank you, Dennis. We can take one question. Sorry. It's good. No, perfect.
Dennis, can you elaborate on the second point, on the depth of the neural nets? I mean, what is your current understanding?
Well, the funny story there was that when we used to have phone calls every quarter with DARPA, and they had some consultants, and we just used the word DNN as a generic, neural network, acronym, and we had that in a slide, and the consultants kept saying, "What are you talking about? This is 2 or 3 layers. This is not a DNN, So obviously it's not deep, but the task at hand wasn't that complicated, right? We're doing a fairly simple, in the first example, classifying the presence of a vehicle or something like that, right? This is not NLP. This is not the kind of task that a lot of you are working on, right? So if the task is simple, then you can use a very, very tiny neural net and put it in a very tiny budget that you might not have thought was feasible to do before, right? If you do it in hardware. And then as you move forward, then the more complicated the task, or if you're pushing the SNR limit, we're finding that our networks have to get a bit bigger to listen at tens of meters distance, things like that. Then things just scale from there. But that was my point there. Okay.
Thank you, Dennis.
Thanks.